Hello, welcome everyone to the analysis seminar. Today's speaker is Hakim Boumaza from Université Sorbonne, Paris Nord. He'll speak about integrated density of states of the periodic Airy-Schrödinger operator. Hakim, it's all yours.
Okay, thank you very much for the introduction, and thank you very much for the invitation to this very nice seminar. So, as you said, today I will present you results on the periodic Airy-Schrödinger operator, and especially on results on the integrated density of states. So this is a joint work with Olivier Lafitte, who is here today, in the audience at least. And this result will appear very soon in Journal of Mathematical Physics by the end of the month. It's supposed to appear. So just a summary of my talk. So first, I will give you a short introduction where I will present you two operators. So the first one is the periodic Airy-Schrödinger operator, which I will define, and then I will define the truncated version of this operator, which will be the multiple Wells Airy-Schrödinger operator, and I will try to explain the links between these two operators and how when we study the spectrum of the second one, we can get the integrated density of states of the first one. So then I will introduce many notations and give you the main results. So I will present you two theorems today. The first one is an eigenvalues counting result for the multiple Wells Airy-Schrödinger operator, and then an exact formula for the integrated density of states of the periodic Airy-Schrödinger operator. And after that, I will take time to give you a flavor of the proofs of these two theorems, and especially the first one, because the second one, as you will see, is an easy consequence of the first one. The first one is really the difficult one to get. Difficult, you will see, technical at least. So I will start with my introduction. So the first thing is to present the operators from which we will study the spectrum. So the first one is the periodic Airy-Schrödinger operator on the real line. So we deal with a Schrödinger operator, periodic Schrödinger operator in one dimension, acting on the Sobolev space H2. And at the beginning, we can put several physical constants, just to say that this kind of operator describes the motion of an electron in a periodic media. And here, the potential which describes the periodic media is very simple, because it is just a piecewise linear and periodic potential. And it's important here to always see to already see that it is not differentiable at its minima points, and actually at its maxima points too. So this is something which makes the analysis of this kind of operator more difficult than usual. So so here we have simply an absolute value up to some constant, and which is we take the periodic version of this. This first, for such an operator which is periodic, we have of course the general result which describes the spectrum as a union of bands, of spectral bands. So this is a classical result for periodic operators. And since we are in dimension one, we have always gaps, spectral gaps too. So here we have, I introduced already some notation. So for each spectral band, I will denote them by EP min and EP max, the spectral band edges here. And of course, we have spectral bands and gaps here. Just to mention that in a previous article with Olivier Lafitte, which appears in the Journal of Differential Equation in 2018, we had very precise estimates in the semiclassical regime, not limit regime, for the spectral band hedges. Hence, we got very precise estimates for the spectral gaps, the length of the spectral gaps, and the length of the spectral bands. We will use it at the very end of my talk. We will use the results on the length of the spectral bands, actually. So that's why I already mentioned it. And Olivier Lafitte gave a talk at this seminar, the analysis seminar, in November 2019 on this subject. So then we are interested, so we have this periodic Airy-Schrödinger operator, and then we are interested in a truncated version of this operator, which is a multiple Wells Airy-Schrödinger operator. So here I will present you the case of an odd number of Wells. So it is the same operator, except that the potential now is no longer periodic. But there is a cutoff, and we consider only 2n+1 periods. And after that, we take 0 for the potential.
Hakim, j'ai une question.
Oui.
Oui, c'est Alexandre. So I was wondering something really trivial. Why is it called Airy-Schrödinger instead of just periodic Schrödinger? What does the Airy part mean in the picture?
Actually, the Airy part, I will just tell it a bit later, but it is because with this piecewise linear potential, to solve it, you will be able to rescale the equation, the eigenvalue equation, and it become on one period, it become an Airy equation. And the Airy function, the classical Airy functions and the not classical Airy, and the Airy function in general, the solution of the Airy equation will play a central role in the analysis. So that's why with Olivier, we decided to call it Airy-Schrödinger operator, because it's really playing, making a central role. The Airy equation plays a central role in this analysis. So
Merci beaucoup.
And another silly question.
Yes.
So sometimes people look at the things called quantum graphs, right? So
Yes.
which is, so the truncated version would be like the graph would be just a single line segment. But right, if you have a quantum graph, then you will have several of them joined at vertices and then with some conditions. So do you think that what you're doing, you could also have some sort of periodic potential sitting on this graph, on a quantum graph, and with some reasonable matching conditions at the vertices, and then you could have a sort of a slightly more general version of this problem, also one-dimensional, but sitting on a more complicated graph?
Okay, that I never thought about it. What I know about quantum graphs is that it's not so one-dimensional than it looks. So it would be a bit more difficult, the analysis, maybe, because usually, from what I say about at the beginning, I'm a specialist of the Anderson model, not so much on. I turn out with Olivier on this kind of subjects. But at the beginning, I was working on Anderson model, and I know that in random quantum graphs, usually the kind of results you get is really in between the one dimension and the two dimension and the multidimensional results. And it's a bit, the techniques sometimes are a bit closer from the techniques that you use in multi-dimension. So I don't know if on a graph, on a quantum graph, it will be so. It would be a real generalization, actually.
Okay. No, I was just thinking because on a quantum graph you also have just the second derivative along an edge.
Yeah, of course.
But something,
so the geometry of the graph would play a role which we do not have on the real line. On the real line, it's much simpler. As you will see, we will use a lot of techniques of differential equations, actually, of classical differential equations. And from what I know, again, I'm not a specialist on quantum graph, but from what I know, it's these techniques is a bit different than what we do in one dimension usually.
But if you have something like, you know, like a triangle or a cycle, maybe that.
Maybe, yeah. If the geometry is very simple, maybe it could be.
To some extent you could, but anyway.
That's a very good question actually, because it's really something we could think. I could add it to the extension.
Sorry for interrupting, but
no, it's a very good question. It's a very good remark and question actually. Thank you.
Thank you.
So what I said, so when we do this truncation, we just have also to put some boundary condition here, and we suppose that the solution, the domain of this operator is the function which are still in H2, the second sublet space on R, and which are equal on the edges of on the limit when the potential of the truncation, when the potential becomes 0. So a first natural question, and it was really the first question that we were asking ourselves with Olivier Lafitte. It was how the spectrum of this multiple Wells Airy-Schrodinger operator fills the spectral bands of the periodic Airy-Schrodinger. So do we have eigenvalues only in the spectral bands, or do we have eigenvalues in the spectral gaps, or and how many eigenvalues do we have? Do we have some density or something like this? Here, I should recall here just before speaking about that, that since this potential here is compactly supported, of course, H2n+1 has only pure point spectrum. It does not have absolutely continuous or single, or in general continuous, not even singular continuous spectrum. It's only pure point, and so we can count eigenvalues. Actually, we can hope to count eigenvalues, and here we will actually prove that we have a finite number and a fixed number of eigenvalues in each spectral band of the periodic operator, of the periodic Airy-Schrodinger operator. And then once we have this localization of the eigenvalues, we wanted to know what is the asymptotic distribution of the eigenvalues of this operator when n becomes large, when n tends to infinity. And in this case, as I will define it later, you get the notion of integrated density of states. So actually, if you are able to count the eigenvalues and know where they are inside of the spectral bands of H, then you can get the integrated density of states. Then I go back to my previous remark. Both potential Vn and V2n+1, they are not differentiable at the minima and maxima points. So it is something new because not new, but most of the known results for periodic operator in semi-classical analysis are done for potentials which usually are at least twice continuously differentiable at their minima points, because they use some approximation and they need this regularity at the minimum, at the minima. And here we don't have that. It's not even, it's continuous, but it's not even differentiable at the minima points. And very few results were known in this singular case, actually. Another remark is that, as you will see, our results will be stated in the semi-classical regime. And this semi-classical regime will be characterized by some explicit constants. And it's not really in the semi-classical limits. So what do I mean by that? That in most papers, you will get, in semi-classical analysis, you will have results like when H tends to 0, you have this expansion for some quantities, like the spectral band energies or the idea as the integrated density of states. Usually it's approximation when the semi-classical parameter tends to 0 or in the limit. Or eventually you will get something like there exists some H0 such that for any value of the parameter smaller, you have this approximation. But usually this H0 is not known. It is not something that can be computed, or even you can get easily an approximation. Here, as you will see, we will get results with explicit H0, with an explicit constant, and the result will be really for every H smaller than this H0, you have this this formula, this exact formula, or this number of eigenvalues in the spectral band of H. So this is a bit different, and it will make the proof much more technical at some point, because we cannot simply take the semi-classical parameter as small as we want. So I will explain you this a bit more when I will have introduced the semi-classical parameter. So this is the introduction, and now I will present you the main results. So since the spectrum of H2n plus 1 is only pure point, what we have to do is to compute eigenvalues, actually. So we consider this equation for E an energy, and we consider the eigenvalue equation here. And we already introduced some parameter in order, some adimensional parameter here, C. And so that with a change of variable, we will get rid of all the physical constants, like the length L0, the reference potential V0, and the Planck constant. So this parameter, you will see it just in the next slide. It corresponds to the height of the potential barrier, and it will play the role of the semi-classical parameter for us. So in our previous paper, we were working with another semi-classical parameter, which was this one minus to the power minus 3 over 2. So here we have the inverse, and we will play with the semi-classical parameter, which will not tend to 0 in the semi-classical limit, but to plus infinity. It's a bit easier for us in this case to do the analysis and the computation with a semi-classical parameter which tends to plus infinity instead of a semi-classical parameter which tends to 0 or which gets smaller. It is just a choice. And so with this semi-classical parameter, what we can do is to rescale everything, and we can rescale the eigenvalues here. So we divide them by the potential, the reference potential, and we multiply them by C. And we can introduce the adimensional version of the potential. And with a change of variable which take in account the length L0, we get this equation which defines the rescaled operator H2n plus 1, and it is now this equation that we'll try to that we will solve. We'll try to solve and at least to count the number of solutions here. And similarly, we define the rescaled periodic Airy-Schrödinger operator, and every field will be in bold type here when it's rescaled. So when needed, I will put it back, this equation. And now, if we rescale again a little bit here, since the potential here is essentially an absolute value, this equation here can be on every interval k plus 1. So everywhere when you have this piecewise affine potential, everywhere when it's linear, you can write it as an Airy equation, actually, up to a rescaling and constants. So that's the reason why, to answer your question, Alexandre, that's the reason why we call it as the Airy-Schrödinger operator. And now, instead of considering the usual AI and BI solution of the Airy equation, here, for the analysis that we do, it's a bit simpler to consider the canonical solution of the Airy equation. So with the Cauchy the usual Cauchy conditions at 0, which is UU prime VV prime at 0 will be the identity matrix. So it is much easier to consider this Cauchy condition than considering directly the classical Airy functions. So that's essentially to have a Wronskian which is equal to 1 and to compute the things after that with easier functions. And there is also something else. It is that the zeros of V and V prime, so the second solution here of the basis, will play an important role as some how do you say, some points. It will be some important values for the semiclassical parameter to describe the spectral bands and to know where the spectral bands are, and to be able to compute, to perform our semiclassical analysis. Actually, we will see that in some sense, the very first one of these zeros, the C0 here, will characterize the semiclassical regime for the periodic, the Airy-Schrödinger operator. And so in the sequel, we will restrict ourselves to energies in the range of CVN plus 1, which means the interval minus C0. So this interval, when C becomes larger, it becomes larger and larger. And why do we do this? It's because in this interval, we can use the results of our first paper, and especially the description of the spectral band edges and the spectral bands and the length of the spectral band. So this is why we have to restrict ourselves to energies in this interval. And now we can, I can already state the first result that we get, the first theorem. So with Olivier, we proved that, so the spectrum of H2n plus 1 is equal to its point spectrum. So we only have eigenvalues, nothing else. And the spectrum inside of this interval minus C0 is included only in the spectrum of the periodic Airy-Schrödinger operator inside of this interval. And moreover, so this first point just says that there is no eigenvalue in the spectral gaps. All the eigenvalues of H2n plus 1 are in the spectral bands of the periodic Airy-Schrödinger operator, and there is no eigenvalues in the spectral gaps. And the second point is that, which is the most difficult to prove actually, is that for each P, and for every C larger than CP, so CP is really a sequence of zeros which is growing. And so if C is large enough, and large enough means C larger than CP, then for all the spectral bands, all the P plus 1 first spectral bands, we have exactly 2n plus 2 eigenvalues inside. So we know we can count the number of eigenvalues inside the spectral bands, and there is no eigenvalues everywhere for sigma H2n plus 1. So just to give the link between these two results, we have to say that we proved in our first paper with Olivier that for C larger than CP here, all these spectral bands for I in 0 to P are actually inside of the interval minus C0. So this
I have a question again.
Yes.
The value of C is the one you gave before with the formula, right?
Yes.
So if H bar becomes large, then C goes to 0, right? Or
if H bar become large, yes, if H bar become large.
Oh yeah, but H bar becomes small. Yeah, okay, sorry. H bar is small.
But if so it's really equivalent to H bar tends to 0. It's just another way to write the semiclassical limit. But when H bar tends to 0, C goes to infinity.
Yes, I read it reverse. Thank you.
Okay. So So here, as I said, for C larger than this constant, is explicit constant because they can be computed. They are not completely explicit, of course, but they are zeros of some classical function solution of the Airy equation. So we know this constant in some way, or at least we can compute them. And for C, each time C becomes larger than the next one of this constant in this sequence, then we catch one more spectral bands inside of minus C0. And inside of these spectral bands, we will have automatically 2n plus 2 eigenvalues for h2n plus 1. So some remarks. So the first one, I already said it, it's that there is no eigenvalue inside of the spectral gaps. All the eigenvalues are in this band spectrum of H. I forgot the bold here. Well, it's true also when it's unbolded. This one, I said it too. And maybe the first point here, as you may see, it does not depend on the value of C. So it is still true, as you will see in the proof, there is always no eigenvalues in the spectral gaps, even if C is very close to 0. But it is not very interesting as long as C is not larger than at least C0. Because if C becomes larger than C0, then the first spectral band is completely inside of the interval minus C0, and there is, and the first spectral gap enter this interval. So if C is not larger than C0, it doesn't tell you something very interesting, actually, because there is no gap inside of this interval. The gap is somewhere in the positive real line. So even if I state it this way, because mathematically it does not depend on the value of C, but it becomes really interesting only for C larger than C0 here. And the last remark I want to do about this theorem is that we could, of course, also define H2n in a very similar way. We would have changed, maybe I just go back to the potential. Here we would have just translate a little bit here the graph to make it even and to have the maximum at 0. In this case, if we take an even number of wells, just to have an even function actually for the potential. And in this case, the result becomes is still valid, and you have instead of 2n plus 2, you have 2n plus 1. So in general, if you have n wells, you will have n plus 1 eigenvalues in each of the spectral bands, as long as C is large enough. Okay, so then I will go to the second result, the result about the integrated density of states. So the integrated density of states of an operator is the distribution functions of its energy levels per unit volume. So it's something which is very common in random operators. We define it through some expectancy, and we count the eigenvalues of some of the truncated operator in some box. And we consider then a thermodynamical limit, which goes when the size of the box goes to infinity. And we get some mean energy values of the number of the energy levels per unit volume. This kind of thermodynamical limit is necessary when you deal with continuous operators, because in general, you don't have a discrete spectrum, but you have absolutely continuous spectrum, or at least you have an infinite number of eigenvalues. And here, the quantity that I state here, this number of eigenvalues, or at least of the spectral values of an operator smaller than some fixed real number, some fixed energy, is usually infinite. So that's why we have to consider a truncation of the operator, so that this number of eigenvalues smaller than some fixed energy becomes finite. And then we have to prove the existence of this limit. So for some operator, at least in a random Schrödinger operator or the Anderson model, it's already a result just to prove the existence of such limits. Here, as we will see, since we have a way to count and to localize the eigenvalues of H2n plus 1, it has become actually not so complicated to compute this limit, to prove the existence, of course, and to compute this limit and get a formula for this limit. So really, now, and the way we wrote the paper is represented like a result on the integrated density of states. But to be really honest, in the history of the article and how we go to the results, we first ask ourselves the questions about the distribution of the eigenvalues inside of the spectral bands. And once we got something simple enough, we realized that it was not too complicated to derive a formula for the integrated density of states for the periodic Schrödinger operator, Airy-Schrödinger operator. So as you will see, this the theorems that I will state in a few slides will be a consequence of theorem 1, and most of the work has to be done to prove theorem 1 actually. So in order to be able to give a formula for this integrated density of states, I will need a bit of notation. So this time I will use again the canonical solution of the Airy equation, U and V, and I will introduce these two functions, capital U and capital V, this way. And these two functions already appeared in our previous paper, since the spectral band edges of H are exactly the zeros of these functions. Not exactly this function, but U minus E and V minus E and their derivatives. So through these two functions and their derivatives, we can characterize the spectral band edges. And it was the core of the analysis to get the semiclassical analysis to get the estimates of the spectral band edges for H. And since the spectral band edges are exactly the zeros of this function and their derivative, if you consider the function UU prime VV prime of minus E, then its sign will change exactly at each spectral band edge. So it will change each time it goes across the spectral band edge. So when it leaves the spectral band to go to a spectral gap, or when it enters a spectral band from a spectral gap, the sign will change. And that's why actually we will prove that this function is negative inside of the spectral band and positive on the spectral gaps. And so that's why inside of the spectrum of H, so in the spectral bands, we will introduce this function, which gives the argument of U prime V plus UV prime plus 2i times the square root of this function, which describes the spectral band edges. So I can almost state the theorem. Just to say that here we have the integer part of a real number x, and one on CD is the characteristic function of an interval. And we are able to prove, as long as the semiclassical parameter is larger than C0, so C0 is the first zero of V prime, smaller zero of V prime. Minus C0 is a zero, is a smaller, the first zero of V prime. Then if C is larger than C0, for any E in the interval minus C0, we have this formula for the integrated density of states. And it comes like, you have everywhere you have a parameter 1/2, it is just because the length of a period is 2. Here, so we divide by the length of a period. So if you forgot about the 1/2, you will get something like the number of bands which are smaller than E. So you have one value of the energy E in minus C0. You have a number PE of spectral band edges which are below E. completely below E. So even if E is in one spectral band, then we don't count the spectral band. It's really all the spectral band which are completely below E, entirely below E. And then if we are inside of a spectral band, the integrated density of states is just 1 over pi phi of E, or minus 1 over pi phi of E inside of the spectral band, depending on if we are in an even spectral band or an odd spectral band. Even and odd refer to the index of the spectral band here.
Hakim, could you remind me what is phi?
Yes, of course. Phi is the argument here of this complex number. So this is, you can write it like an arctangent if you want, because this number here will be of modulus 1 because of the Wronskian of U and V is equal to 1. U and V are both solution of the Airy equation. I forgot to tell it. They are both a solution of the Airy equation, as their Wronskian is equal to 1. So here, this complex number has modulus 1, and you can get a formula in terms of arctangent 2 times arctangent of square root of UU prime minus UU prime over VV prime, so if you want. But we will really use it like an argument here of here. And as we prove it later, the function phi here will be monotone. It will be increasing on the even spectral band and decreasing on the odd spectral band.
Thank you very much.
So that's why we have here, since it is increasing on even spectral bands, you have here 1 over pi times phi. And if it since it is decreasing on odd spectral bands, you have minus 1 over pi phi. Because of course the integrated density of states, I forgot, even if it's completely evident, from this formula, of course, it's an increasing function. It's an increasing function. When you E increase, you have, this cardinal here, this number of eigenvalues is just increasing. So, so we have this explicit formula. We have a formula for PE, the number of eigenvalues, but it's not very important, this one, actually, for what we had. And I just give you just an image, a graph here. So this formula, you can just compute it on Maple, for example. So I did it for C equal to 2.8 because in this case you are already larger than C1 and you already have 2 spectral bands here. So on the spectral gaps, these functions, like every IDS, is constant, and it is increasing on the spectral bands. So on the spectral bands here, we see that it is increasing, and is increasing this way. Of course, C equal 2.8 is strictly larger than C0. C0 is around 1.515. And so here you have the 2 first spectral bands. So a few comments on these results. So theorem 3 will be a consequence of the first theorem, this theorem. I don't know. Yeah. It's because it gave number with the definition, because we only have 2 theorems here. Another remark is that this formula can be seen as an extension of Shubin's formula. Shubin's formula is for smooth potential. It's much more general, but it applies for smooth potentials here. And here is some extension of Shubin's formula to a non-C1 potential, not even differentiable at its minima. And the Shubin's formula states that the IDS is equal to the quasi-impulsion divided by pi, sorry, and here the quasi-impulsion is given by the function phi, actually. It's also very similar to the formula given in the paper by Schenk and Shubin. and for which also was for smooth periodic potentials, not for non-differentiable potential, but the formulas are very similar. And they were giving a formula in which we had for the IDS something on the interval here. We had 1 over pi times the arc cosinus of the Hill determinant. So the problem is that here, since we have some problem of singularity, the Hill determinant is a bit complicated to define. It's possible, but I think it's a bit more complicated. We cannot directly apply the results. But here, even if we cannot apply directly the results of Shubin and Schenk and Shubin before, we are able to recover these results from scratch, because we can really compute the solution and give expression of the solution of the eigenvalue equations with classical Airy functions. Okay, so I still have a bit of time to give you some ideas of the proof. So I will not go into the details, even if I have a lot of slides. I will go a bit faster. So the first idea, the first thing to compute the spectrum of H2n plus 1 and to prove theorem 1, the counting result of eigenvalues, is to solve this equation for E in minus C0. For this, we consider even and odd solution defined like this through U and V, and capital U and capital V, and these two functions here from a basis of C1 solution of this equation of the eigenvalue equation for H2n plus 1. Hence, we can write any solution as a linear combination of these two equations on each interval, on each period, here on each interval 2n minus 1, 2n plus 1. And we can give the relation between these coefficients, an and bn. They are linked through some transfer matrix here. Then we can compute which maps the coefficients on the interval for n to the coefficients, so to the solution for the interval at n plus 1. And in particular, we can see that the coefficients at minus n, the coefficients, sorry, at n are given through the coefficients at minus n up to a power of this transfer matrix here. So one of the things we will have to do is to compute this power of this explicit matrix here. First thing is that since after 2n plus 1 on 2n plus 1 plus infinity, the potential is 0, and we know that the solution have to be L2, we have a solution of this form. So we can solve explicitly, of course, the solution in this case is just minus the second derivative equal to EU. And so we have such a solution here with lambda, a positive real number, which is such that lambda over C is equal to the square root of minus E. Here I recall that E is in minus C0, so minus E is positive. Then considering the Cauchy-Lipschitz theorem, one can choose phi such that phi 2n plus 1 is equal to 1. So it is just equivalent to enforcing the Cauchy conditions at 2n plus 1. So we have phi 2n plus 1 phi prime to s plus 1, which is equal to phi 2n plus 1 times the vector 1 minus lambda. And if you write this in terms of the solution here, we will get these two equations. So we have these two equations here, and it leads to introduce this function phi of y here. And if we have this big function, which is just this system of two equations written in one function, I recall that lambda is equal to y plus c, square root of y plus c in this case, and sorry, I go maybe a little bit too fast, but if we introduce this function phi, then these two equations here are equivalent to phi of minus c minus e equal to 0. So we are bring to find the zeros of this function, actually. And so for this, we have also to compute the coefficients an, bn before. So we also, to compute the coefficients an, bn, we will use the transfer matrix. We can also use the fact that at minus n, we can directly solve the system to get this expression. And then computing the power to 2n plus 1 of the transfer matrix, we get several different expressions for the function phi here, because we get several expressions for the coefficients an and bn. And it will depend on if the energy E is in a spectral gap or in an even spectral band or in an odd spectral band. So what we do is that in the sequel, we will consider the spectral band in terms of energy or in terms of this new variable y here, because it will be a bit simpler just to look at the zeros of phi. And we can set y equal to minus c minus e. And in this case, the spectral band become yp max and yp min. I just write it in this way because of the minus in front of e, so that we really get this. Maybe I will go a bit quick on all this notation. So we have a lot of notation in order to be able to write the expressions. It's not very important to remember the expression, maybe just the first coefficient a here, which is the real part of the number from which we take the argument in the definition of phi. Then, depending on the sign of UU prime or BB prime, we defined several. We define B0 and B1, and we have B, which is just the imaginary part of the number, which we take the argument in the definition of phi again. Then, just in order to be able to write the expression, I introduce some functions here. The function k will be useful later. It will be an increasing function on every even spectral band edge. And the other function, alpha and beta here, are just positive functions because you have a square root and a square here. So they don't really matter, actually. So we get, after some computation of the power of matrix power, we get a very big expression for phi. For example, in a spectral gap, so when UU prime and BB prime are strictly positive, we get such an expression, a bit complicated, with A and B, the real and imaginary part of the real numbers that we took in the definition of phi, and here this expression, this quantity, which is positive. So with such a big expression, actually, to prove that there is no eigenvalues inside of the spectral gaps, we just have to study the sign of phi. And to study the sign of phi, I will come back for the spectral band just after, but now I'll just show you, because we know actually the sign of UU prime, VB prime, if you are in a band or in a gap. It will depend on some on the index of the spectral band modulus 4. So it's a bit complicated. The only thing you have to realize is that you have two kinds of gaps. You have the gaps where the simple gaps, I will say, it is where UU prime and BB prime have all the same sign. For example, they are all negative or they are all positive. Here I have another gap when they are all positive. So you have this kind of gaps. In this case, it is very easy to prove that phi is, with this expression, is actually strictly positive, because this product here, u prime plus some square root times u, and v prime plus some the square root of y plus c times v, is positive, or both are positive or both are negative. And then in this case, the product is always positive, and it's easy to prove that since in a spectral gap, you will have a b strictly smaller than the absolute value of a, you will prove that everything is positive here. And in this case, it's not complicated. A bit more complicated is when you are in a gap when u prime are negative and v prime are positive, or the opposite. In this case, this product, the product of this first term here, will be negative, and you have to show that actually this quantity is negative too. And it's a bit more tricky, and it helps to have 2n plus 1 being odd here. In the even case, you have to deal a bit different, and the signs are different actually if you have a power 2n. And so again, it is just about studying the sign of this expression, but you prove again that in the second type of spectral gaps, you have phi, which is strictly positive. So in all the cases, you don't have zeros for the function phi in spectral gaps. Now, if we are in a spectral band, it's a bit different because u prime will be strictly negative and v prime will be strictly positive. If we are for an odd spectral band, it is just the opposite. And you have again a big expression with complex number, conjugated complex number, and the function k, which will play a role here. And what is important is that you have this tangent of 2n plus 1 times phi, actually, times this argument of a plus ib is just phi, actually. Not exactly phi, but it's phi of y plus c on some other. I will introduce the good function, but it's almost phi up to a change of variable. And what will help us to count the number of zeros of phi here is that this tangent has singularities, and we will prove that the zeros are between two successive singularities of the tangent. And after that, we have to take care of all the other terms, but I will show you on some graphs, some graphics, what happens. So what we do is that we introduce the function phi again, but with a good variable, this one, and we perform the change of variable y equal to minus c minus e. And we prove that this function is, in order to be able to use this tangent here and to work with this tangent here, we prove that this function phi tilde is a strictly decreasing homeomorphism on even spectral bands, and a strictly increasing homeomorphism on the spectral band, on odd spectral band. So the first thing is to prove this, actually. To prove this, you do some computation, actually. This is the most technical part. This is actually what took us most of the time. And you get, you first give some exact formula here for phi tilde, some expression for phi tilde. Then you want to study the derivative of phi tilde, so you compute it. You see that the functions which are involved here are a bit complicated because y is in every terms here. And so when you compute the derivative up to y, you will get some complicated expression. But all these expressions are bring to just one thing: to study the variation of phi tilde, you have to know the sign of some function h of y here, which is given by this formula. So this formula at first sight, it seems simple because you have u prime, v prime, again u prime, v prime, and uv, and you know the signs of these functions. But what makes the things difficult is that when you are in an even spectral band, you will have different signs for these four functions. And what makes things even more difficult is that you have these two coefficients, this y here and y plus c here. And the most difficult part actually in our analysis was just to compute the sign of H, just to prove that H is positive on even spectral bands and negative on odd spectral bands. So this is the most technical part. Actually, if I have a few minutes at I will give you some elements. So once you have this result, you have you can just study the zeros through like the zeros of a tangent of 2n plus 1 x. So if you study now the function tangent 2n plus 1 phi tilde y, you see that it will vanish at the spectral band edges, and you will have 2n zeros inside, in between the singularities of the tangent of inside here. So you consider here the reciprocal image of pi over 2 to 2n plus 1, because you have 2n plus 1 here. And you can just count here the zeros. You have already 2n plus 2 zeros. But of course, it's not exactly the function phi. So now we have to multiply by some function of k, which is k square minus 1 over k square plus 1. And we have after that some, we had the function 2k over 1 plus k square. So k square minus 1 over k square plus 1 is a function which is positive at the beginning, then becomes negative, and then is positive again. So it will change the signs when you multiply this graph here by this graph, the red graph here. You will change the variations this way. At the beginning, it's the same because k is positive. Then when k, not k, but k square minus 1 over k square plus 1, when this function becomes negative, then you will have a change of variation, and the function will start here to change the variation at some point. And after that, the graph will become increasing. Then when k becomes positive again, you will have another change of variations. And what it makes here is that it adds 2 zeros. Multiplying by this function here in front of the tangent will bring you to 2n plus 4 zeros. So now we don't have the result, but we have not finished. The next part is to add this function here. But this function here, if you look carefully at the signs, we see that actually it will just be a translation of this graph here, and you don't have and you don't add or remove any zero actually. So you still have 2n plus 4 zeros when you had the term. And what gives you the right number of zeros at the very end is that what you do if you look at the formula, I will just go back at the big formula here. In the front here, you have some cosinus of this. And so you remove some singularity when you remultiply by the cosinus here. And the only effect it has is that it will actually remove the zeros at the spectral band edges. So the two first zeros that we had at the spectral band edges, one will become negative, the other one will become positive as the value of the function. And so you only have the 2n plus 2 zeros inside of the spectral band edge. So that's how we prove the counting result of the eigenvalues. And once we have this counting result, then it becomes very easy to get the formula for the spectral bands, because as we see, all the eigenvalues are in between two singularities of the function tangent 2n plus 1 phi. And so we are able to put these eigenvalues. We know that in between two singularities of these functions, we have 0 or 1 or eventually two eigenvalues. The two eigenvalues happens only twice, and the 0 eigenvalues happens only twice too at the edges of the spectral band. And so we know exactly how many eigenvalues we have and where they are. And so what we know is that if we take an energy inside of the spectral of an even spectral band edge, then they are exactly the number of singularity plus 0, 1, or 2. No, not the number of singularity, sorry. The index of the interval you have of the, if you arrange in order the singularities, you can then put index on the intervals you get, and it allows you to count the number of eigenvalues smaller here than some energy inside of a band, and you get directly the limit like this. So it's really the pi appears here as because the tangent will have singularities at pi over 2 over 2n plus 1 here. So that's how you get the formula for the IDS. So really the big part of the job is to be able to count the eigenvalues, really the first result. And now if you allow me some minutes, I will just finish a few remarks. So just in odd spectral bands, you do the same, but since now phi is decreasing, you have to count the eigenvalue from the other side. So you go in decreasing order, but it's the same kind of computation. And just a few words about the proof of lemma, which was very complicated, the proof of lemma of the sign of the function h, because this is really the most complicated part. So here, the idea is the following. Due to the results we had in our previous paper with Olivier, the spectral band of H are centered at the zeros of the classical AI function and its derivative. We also know, then we prove that for C larger than C0 or CP, when we are in the piece spectral band, H is positive or negative at this center, at this 0. And then we use that the length of each spectral band is exponentially small, and so by Taylor formula, the sign will not change on the spectral band. So that's the idea. Just to give you a flavor, you get very big expression like this. On such expression, you can see that if you can take C large enough, as large as you want, then it's become very easy to get the sign, because the dominant term is this one, and it's positive on an even spectral band. But we want to get the result for C larger than CP, and then it becomes much more complicated, because you have to be able to compute the sign even for C close to CP. And then you have to use a very complicated approximation in J for all this term here. So of course I didn't put them on slides because it's just too complicated. And then you also have to use approximation of the length of the spectral band of H that we got in our previous paper, and which are exponentially small. And again, we have to use some kind of approximation like this, just to get the positivity of H, not for C arbitrarily large, but for C larger than CP. And that's what is very, very complicated. Okay, so we really see, just as a conclusion, we really see that C0 plays a central role here, because the formula of the IDS is valid as soon as C is larger than C0, and theorem 1 becomes interesting as soon as C is larger than C0, because in this case the first spectral gap enters the interval minus C0, and the first spectral band is entirely inside of the interval minus C0. And so we know that there is 2n plus 2 eigenvalues in it. So we can say that this constant C0, so 1.515, really characterizes the semi-classical regime for the periodic Airy-Schrödinger operator. Again, what is very difficult, and it's really seen in the proof of the lemma for the sign of H, is that we really get these results for C as close as we want from C0 and the other constant CP, and not C arbitrarily large. And for C arbitrary large, the lemma becomes very simple. It takes half a page. And here in the paper, it takes more than 8 or 9 pages just to compute the sign. Okay, and just to finish this, one open questions that we are starting, we have already started to work on it, but we want to be able to travel again to meet with Olivier one day to be able to generalize these results, not only for potential, which is the absolute value of X, but for this absolute value of X taken inside of some analytic functions with some condition at 0. Okay, so I just put some references or 2 papers here, and the Bible, Abramowitz and Stegun, which gives all the formulas and the asymptotic development for the Airy functions, which were incredibly useful to prove the lemma. And the paper of Schenk and Shubin about general theory. And I will finish. Thank you for your attention. And I hope that we may meet in reality some days. maybe not too far, maybe next year if I am able to travel. I think I will go to I was supposed to go to Montreal in June, but it wasn't possible to do it. Okay, thank you.
Thank you very much.
Thanks.
Are there any questions?
If someone may I add a comment.
Of course.
The comment is the following. When we mathematicians discuss on this type of problems, we speak of integrated density of states. What physicists look at generally is what they call density of states. And when we look at what they do, it's exactly the derivative of the function that Hakim and I derived. But they do not have this case as well, and they have very few explicit cases where you can have the DOS explicitly calculated. So I think this type of result and this type of study would be useful to draw a bridge between the physicists of this type of work and the mathematicians. So that was my principal comment on that.
And can you have, so there is a density of states, but there is also sometimes a spectral function, right? So the kernel of the spectral projector.
Yes.
Is it, so it, in your case, you should also be able to write it down, right?
Yes, we have not done it, but yes, because the IDS is just a trace of this spectral function. So yeah, we should be able to write it indeed.
Probably also in terms of maybe some sort of modified, you know, solutions of Airy equation or.
Yeah, very interesting. I have not had this in mind, but it should be accessible. From what we have done, it should be not too complicated to compute it.
Because sometimes, you know, also if you look at like Laplacians on manifolds or something, then people look at the eigenvalue counting function. Of course, that's the first thing they study. But sometimes it's also interesting to look at the spectral function, and so that is at least sort of more in my neck of the woods. Like with some of our colleagues, we looked a little bit at these things. Yeah, but it seems that your solution, like the last question, you look at your solution, if you add, you know, some sort of smooth function to what you are doing, then your solution would be like the leading term, and then you will have some corrections from the smooth or something.
Yes, that's the idea. If you look at the generalization we want to do, of course, what will in this case, what we want to do is, that's why we have to suppose that this analytic is just to take the leading term and to be able to prove that the other terms don't play really a role, of course. But again, it's very difficult actually to have the estimates on the other terms.
Yeah, no, I understand, because such explicit may not be true, right? I mean,
yes.
Once you add. But and maybe, I don't know, my last very naive question. Suppose your potential has a jump discontinuity, so it's even worse than what you are doing, right? Can one do what can one do in that case? I mean,
I think that we don't lose so much. It will be a bit more complicated because at the very beginning, we cannot write exactly the same way the function phi, because we really use some, maybe I say something wrong. Maybe Olivier will help me on this case, but no, the solution will still be continuous, even if we have the discontinuity.
If the potential is discontinuous, then the solution is continuous because it's in H1 and we are in 1D. So I think that
Sobolev theorem still applies. So yes, the solution will still be continuous actually. So
and I think that's the way people do in physics. In general, they look at boxes where they put 1 in a box and 0 outside the box, and they repeat the motive. And so when physicists compute the DOS, they just use this type of question, Dima.
Okay. All right, so are there any other questions or comments? Well, if not, let's thank Hakim again for a great talk.
And hope we can see Hakim in person in the streets of Montreal in the near future.
Yeah, I hope so.